We are now discussing about context-free grammars representing context-free languages, and from this topic till now we discussed about context-free grammars, how strings can be derived and the language represented can be identified, and also we have seen how to prove the correctness of a grammar which has two parts, soundness and completeness. This is what we did till now. Today we are going to see some more aspects about context-free grammars, and the agenda for discussion today includes leftmost derivations, parse trees and ambiguity related to context-free grammars. We know that derivation is the process of deriving a terminal string or a string in the language from the start simple of a grammar by applying a finite sequence of productions or rule. Now we can see what is leftmost derivation, and the name itself gives a hint what it is. We can try to understand what are leftmost derivations using an example grammar and derivation of a string in that grammar. Here is a context-free grammar given with the 5 rules or productions. Only one variable is there, which is capital S, and these are the terminals. Now look at a derivation. We have to start with the start simple, and in the first step we are applying production number 1 for S. So S is replacing, S can be replaced with the RHS. That is what we do. Now suppose you apply production number 3, which is this, on this S. So you are replacing this S with small a. Then suppose the only variable S is replaced by applying production number 2. 2 is S star S. That is what you do. Then next you are applying production number 4 on this S. What is 4? S is replaced with small b. And finally we are applying production number 5 on the last S, which replaces capital S with a small c, and thus we derived a terminal string which is a plus b star c. Now if we recall what we did, to start with we started with the start simple of the grammar, then we replaced that with a production, here production number 1. Now see, here you have 2 variables. Now the question is, for which variable you are going to apply a rule or a production. In this example we applied the third rule for S, and the first S is replaced. Now in this case only a single variable is there, no doubt you can replace that, and what we applied for that S is rule number 2. So you replace that with S star S, and here again there is a confusion. There are 2 variables, both are S, but which S to replace? And in this example we decided to replace this one by the rule 4, so which tells you can replace capital S with small b. That is what we did. And once you reach into this, no doubt here only one variable, we applied production number 5 for that variable. So you are replacing capital S with small c, deriving this terminal string. And now see that every time we decided to apply a rule for the leftmost variable in the current sentence, which is what is called a sentential form. And this kind of a derivation where the leftmost non-terminal is replaced at every step is called a leftmost derivation. It's a very simple definition. So, because context-free grammars allows to have any string in the RHS of a production, including variables and terminals. Now, at every step, if you replace the leftmost variable or non-terminal, another name of non-terminal is variable, then the derivation is what is called leftmost derivation. Now, there is something called a parse tree. With the same example, we can try to understand what is a parse tree. So, here is that grammar, and now you look at the derivation again. We started with the start simple, and you can model it, you can model the derivation process with a tree. When you start with the start simple, you are starting with a root node whose label is the start simple. Now, if you recall what we did in the first step is this, that is, we applied production number 1 on this S, we obtained this, and this can be simulated or represented in the tree like this. So, what is it meaning? Previously you had only a single node S, now you can expand this S which is a variable, which is representing a variable or a non-terminal with the RHS of a production. So, what is the RHS of this production? This is the production, and you can represent this string by child nodes for the node with the root node S. So, in this case, the number of children will be the number of simples in the RHS. So, this is how you will represent it. Now, we applied rule number 3 for the leftmost S. So, here you can say that in this case you are expanding this variable node with the RHS of the production 3, which is A. This is what you are getting, and not that a terminal node cannot be expanded further. You cannot expand because there is no rule where the terminal is the LHS. Now, here only one variable, you applied this production, and what you can do here, it means that this variable node is expanded with the RHS of the production 2. So, you will get 3 child nodes here in that order, S star and S. That is what you do. And here you applied on the first S production number 4. So, you are replacing capital S with small b, and the leftmost S is what you are replacing always. And here if you look from the left, the leftmost variable node is this. You are applying production number 4, that means you can expand it with a single child which is a terminal node. Now, you see that only one variable, and you apply production number 5, if you recall from the previous slide. So, you replaced capital S with small c. So, what you do here, only one variable node is going to be expanded with production number 5. So, this will get one child node. And now you see that you cannot proceed further in the tree because now there is no variable node as a leaf node. Every leaf node is a terminal. So, you finished. So, we can see that leftmost derivations and parse trees represent each other. Given a leftmost derivation, you can automatically see what that parse tree is and vice versa. So, they are kind of equivalent representations. And now I can tell you why these are called terminals A plus B star and C, because they are terminal nodes. The derivation process using the tree terminated with the terminal node on that path. Okay. So I hope you are getting leftmost derivations and parse trees. Parse tree is a representation of a leftmost derivation. Now we can ask this question, which is a very important question. Later we can see that when the answer is yes, we are getting a manageable grammar for answering various questions. Otherwise, certain questions about that grammar is going to be difficult to answer. So the question is this: given this grammar with 5 productions, exactly the previous grammar, is the leftmost derivation unique for this string? This is the string that we have derived, and this is what the derivation we have seen. This is a derivation. Unique means, is this the only way you can derive it? Can you apply any other sequence of productions? Here the sequence of productions from the start simple applied is 1, 3, 2, 4, 5, where in each step you replace the leftmost variable. Now the question is it possible to have another leftmost derivation, that is a different sequence of productions, which will let you derive the same sentence? Here the answer is yes, you can have another one. See that here you started with production number 1, here you started with production number 2. The productions applied are 1, 3, 2, 4, 5, that is the sequence here. 2, 1, 3, 4, 5 is the sequence applied here. So, 2 different leftmost derivations are there. And this kind of grammar allows you to have multiple leftmost derivations for a terminal string. So, it is not unique, there exists more than one derivations. We have these 2 at least. This type of a sentence or terminal string for which there are more than one leftmost derivations is called an ambiguous sentence. There is an ambiguity in deriving that sentence. You cannot say you must have to apply production number 1 as the first step. You can either use 1 or 2. So, it is an ambiguous step then, which one to select. I hope the definition of ambiguous sentence or ambiguous terminal string is clear. When that string can be derived using more than one leftmost derivations. And a grammar is called ambiguous when it derives an ambiguous sentence. If there exists at least one ambiguous sentence or terminal string in the language of the grammar, then the grammar is said to be ambiguous. So, these are very important concepts in the language theory and formal representations using grammar. We saw that leftmost derivations and parse trees represent each other, a kind of equivalent. So, given this leftmost derivation, this is the unique parse tree representing this, and we have seen another leftmost derivation for the same sentence, and this is this parse tree for this, and see that they are different. Here you are applying S plus S as the first rule, here S star S, and you can see that these two are different trees. So if you have two different leftmost trees, it's very clear you have two different parse trees. So you can define ambiguity in terms of parse trees as well. Now you can say that a context free grammar is called ambiguous if there exists more than one parse trees or derivation trees for a sentence in the language represented by the grammar. So here you have two parse trees, so the grammar is ambiguous. And if you have two parse trees, definitely you will get two different leftmost derivations and vice versa. And with this, we are finishing this lecture, and I am giving you an exercise problem for you to practice and understand what are ambiguous context free grammars. You are asked to provide an ambiguous context free grammar and then argue that what you have proposed is an ambiguous grammar. So you have to find a sentence which is ambiguous. Today we discussed about leftmost derivations, parse trees and ambiguity. We saw that leftmost derivations and parse trees represent each other, and a sentence is called ambiguous if there exists more than one leftmost derivations or equivalently more than one parse trees or derivation trees. And grammar is called ambiguous if there exists at least one ambiguous sentence or terminal string in the language represented by that grammar. With this, we are finishing this lecture. Thank you.